Before we dive into this journey, please take a moment to hit that like button and subscribe to the channel. It helps us bring more mind-bending stories like this to you. Now, let me begin. The biggest galaxy we have ever discovered is so large that your brain will struggle to truly understand it. This is not an exaggeration. This is not dramatic storytelling. This is the honest truth about a cosmic monster that sits over 1 billion light-years away from us, quietly existing in the darkness of space, holding more stars than you could ever count in 1 million lifetimes. If you are anything like me, you probably thought you understood how big things could get in space. You have seen the pictures of Jupiter dwarfing Earth. You have heard how our sun could fit 1 million Earths inside it. You might have even wrapped your head around the fact that our Milky Way galaxy stretches across 100,000 light-years from one side to the other. But all of that, every single comparison you have ever heard, becomes almost meaningless when you learn about what astronomers found hiding in a distant corner of the universe. Let me set the stage for you. Our home, the Milky Way, is what scientists call a barred spiral galaxy. It has beautiful curving arms made of stars, gas, and dust, all swirling around a central bulge where an enormous black hole sits. From one edge to the other, our galaxy measures roughly 100,000 light-years across. That means if you could somehow travel at the speed of light, which is the fastest anything can move in our universe, it would still take you 100,000 years to cross from one side of our galaxy to the other. That is already almost impossible to truly grasp. 100,000 years is longer than modern humans have existed. It is longer than the time since we first learned to paint on cave walls, longer than every civilization that has ever risen and fallen on Earth combined. And yet, that is just the width of our own little corner of the cosmos. The Milky Way is home to somewhere between 200 billion and 400 billion stars. Each of those stars might have planets orbiting around them, moons circling those planets, asteroids tumbling through space, and comets streaking through the void. Our sun is just one of those hundreds of billions of stars, sitting about 26,000 light-years from the galactic center in a quiet neighborhood called the Orion Arm. Our sun and its family of planets orbit the center of the galaxy at a speed of about 500,000 miles per hour. Even at that tremendous velocity, it takes our solar system about 250 million years to complete a single lap around the galactic center. Astronomers sometimes call this period a cosmic year or a galactic year. In the entire time that dinosaurs roamed the Earth, our solar system did not even complete one full orbit. The last time our sun was in roughly this position in the galaxy, the most complex life on Earth was simple marine organisms. That is how vast even our own galaxy is. The space between stars in the Milky Way is almost unimaginably empty. Our nearest stellar neighbor, a small red dwarf called Proxima Centauri, is about 4¼ light-years away. That distance is so great that if you shrank the sun down to the size of a grain of sand, Proxima Centauri would be another grain of sand sitting about 4 miles away. The space in between would be essentially void, just the faintest wisp of gas and dust and the occasional particle of cosmic radiation. This emptiness is hard to wrap your mind around. We live on a crowded planet surrounded by billions of other people, sharing space with countless other living things. We are used to density, to things being close together, to the world being full. But step outside our solar system, and emptiness becomes the rule. Stars are separated by such vast gulfs that the chance of any two of them colliding by accident is essentially zero. Galaxies can pass through each other without any stars actually hitting one another. Yet somehow, even in all that emptiness, there is enough stuff out there to make hundreds of billions of stars in our galaxy alone. The gas and dust between stars may be sparse, but spread across thousands of light-years, it adds up to enormous amounts of material. New stars are forming right now in giant molecular clouds scattered throughout the Milky Way, places where gravity has pulled enough gas together for nuclear fusion to ignite. Our galaxy is alive with stellar birth, even as old stars burn out and die. When you look up at the night sky from a dark location, that hazy band of light stretching overhead is actually the combined glow of billions upon billions of distant stars in our own galaxy. Ancient people thought it looked like spilled milk across the heavens, which is where the name Milky Way comes from. For most of human history, we assumed that was everything. We thought our galaxy was the entire universe. Different cultures had different explanations for that band of light. The ancient Greeks told stories of milk spilled from the goddess Hera's breast. The Romans called it the Via Lactea, the Milky Road. In India, it was seen as the path souls take on their journey to the afterlife. Aboriginal Australians saw it as a river in the sky. People throughout history have looked up at that same band of light and wondered what it might be. When the first telescopes were turned toward the Milky Way in the 17th century, observers began to realize that the milky glow resolved into countless individual stars, too faint and too numerous to see with the naked eye, but visible through the magnifying power of glass lenses. This was the first hint that our galaxy was far larger and contained far more stars than anyone had imagined. It was not until the 1920s that an astronomer named Edwin Hubble proved that those fuzzy smudges people had been seeing through telescopes were actually entire galaxies themselves, each one containing billions of their own stars, each one impossibly far away from us. That discovery changed everything we thought we knew about our place in the cosmos. Hubble made this discovery at the Mount Wilson Observatory in California, using what was then the largest telescope in the world, a reflector with a mirror 100 inches across. He was observing a class of stars called Cepheid variables in what was then called the Andromeda Nebula. These stars pulse in brightness with a regular period, and by measuring their apparent brightness and pulsation rate, Hubble could calculate how far away they were. The result was shocking. The Andromeda Nebula was not a cloud of gas within our own galaxy as many astronomers had assumed. It was roughly 1 million light-years away, far beyond the edges of the Milky Way. It was an entirely separate galaxy, an island universe of stars in its own right. Our galaxy was not the whole cosmos. It was just one galaxy among many. We now know that Hubble's original distance estimate was off by about a factor of 2. The Andromeda Galaxy is actually about 2.5 million light-years away, not 1 million. But the basic conclusion was correct. The universe was vastly larger than anyone had imagined, filled with countless galaxies, each containing billions of stars. Today, we estimate that there are around 2 trillion galaxies in the observable universe. 2 trillion, that is a 2 followed by 12 zeros. Each of those galaxies contains billions or even trillions of stars. The numbers become so large that they stop meaning anything to our human brains. But here is what makes this story interesting. Not all galaxies are created equal. Some are tiny dwarf galaxies with just a few billion stars. Others are massive spirals like our Milky Way or our nearest large neighbor, the Andromeda Galaxy. And then, sitting at the extreme end of the scale, there are the true monsters of the universe, galaxies so enormous that they make our Milky Way look like nothing more than a speck of dust floating in an empty warehouse. Galaxies come in many shapes and sizes. The most common type in the nearby universe are spiral galaxies like our own, with their distinctive pinwheel arms and flat rotating disks. These galaxies are typically sites of active star formation, with new stars being born in the gas-rich spiral arms. The beautiful structure we see is maintained by a balance between the rotational motion of the disk and the gravitational pull of all the matter within. Elliptical galaxies are another major type. Unlike spirals, these galaxies have no particular structure. They range from nearly spherical to highly elongated oval shapes, and they are populated mainly by old red stars. Star formation in elliptical galaxies has largely ceased, as they have exhausted most of their gas supply. The largest galaxies in the universe are almost all elliptical, formed through the merger of multiple smaller galaxies over billions of years. There are also irregular galaxies which have no defined shape at all. These are often the result of gravitational interactions with nearby galaxies which have pulled and distorted their structures. Galaxies are not distributed randomly through space. They are organized into larger structures. Galaxy groups contain a handful to a few dozen galaxies. Our own Milky Way belongs to the local group which contains about 80 known galaxies, including Andromeda and several dwarf galaxies. Galaxy clusters are larger still, containing hundreds to thousands of galaxies bound together by gravity. And the largest structures of all are superclusters, vast assemblages of galaxy clusters stretching across hundreds of millions of light-years. The galaxy I want to tell you about today is one of those monsters. It goes by the somewhat boring name of IC 1101, which comes from its entry number in a catalog of celestial objects created over a century ago. But do not let the dull name fool you. There is nothing boring about this cosmic giant. IC 1101 sits at the center of a cluster of galaxies called Abell 2029, located in the direction of the constellation Virgo as seen from Earth. When astronomers point their telescopes toward this region of the sky, they see a massive collection of galaxies all bound together by gravity, dancing around a common center. And right in the heart of that cluster, dominating everything around it like a cosmic emperor on a throne, sits IC 1101. This galaxy is estimated to be somewhere around 4 to 6 million light-years across. Let that sink in for a moment. Our Milky Way, which already seemed impossibly large, is only about 100,000 light-years wide. IC 1101 is roughly 40 to 60 times larger than our entire galaxy. If you placed IC 1101 where our Milky Way currently sits, it would not just engulf our galaxy. It would swallow our entire cosmic neighborhood. The Andromeda galaxy, which is about 2.5 million light-years away from us, would find itself inside IC 1101's massive body. The Triangulum galaxy, another neighbor of ours, would also be consumed. All of the dozens of smaller dwarf galaxies that orbit around us, places like the Large Magellanic Cloud and the Small Magellanic Cloud, would simply become tiny components of this giant's vast structure. But size is just the beginning of what makes IC 1101 so incredible. This galaxy is estimated to contain around 100 trillion stars. 100 trillion. Our Milky Way has maybe 400 billion stars at most. That means IC 1101 has roughly 250 times more stars than our home galaxy. If you started counting stars in IC 1101 1 star per second without stopping, it would take you over 3 million years just to count to 100 trillion. And that is assuming you never slept, never ate, never took a break of any kind. The story of how we discovered this cosmic giant begins back in 1790, when a German-born British astronomer named William Herschel was systematically scanning the night sky with his telescope. Herschel was one of the greatest astronomers of his era. He had already discovered the planet Uranus several years earlier, and he spent much of his life cataloging thousands of celestial objects that no one had ever documented before. On June 19th of that year, Herschel pointed his telescope toward a region of sky in the constellation Virgo and noticed a faint fuzzy blob of light. He carefully recorded its position and moved on to the next object. At the time, Herschel had no way of knowing what he was actually looking at. The technology did not exist to measure how far away this object was. The scientific understanding did not exist to recognize that it was an entire galaxy separate from our own. Herschel simply logged it as another nebula, one of many mysterious cloud-like objects scattered across the heavens. For over a century, that faint smudge of light remained a mystery. It was eventually given the designation IC 1101 when it was included in a catalog called the Index Catalog, which was an expansion of an earlier list of celestial objects. Astronomers studied it when they could, but without the tools to understand its true nature, it remained just another entry in a long list of cosmic curiosities. Everything changed in the 20th century when astronomers developed better telescopes and new techniques for measuring cosmic distances. They discovered that IC 1101 was not a cloud of gas within our own galaxy. It was an entirely separate galaxy, mind-bogglingly far away. The light we see from IC 1101 today left that galaxy over 1 billion years ago. It has been traveling through the void of space for more than 1 billion years just to reach our telescopes. When that light began its journey toward us, life on Earth was still mostly single-celled organisms. Complex animals had not yet evolved. The dinosaurs would not appear for another several 100 million years. Every major event in human history, from the first civilizations to the invention of the telescope itself, happened while that ancient light was still crossing the emptiness between galaxies. As astronomers continued to study IC 1101, they began to understand why it was so incredibly massive. This galaxy did not grow to its enormous size through normal processes alone. It became a giant through an act of cosmic violence that has been happening for billions of years. IC 1101 is what scientists call a cannibal galaxy. It has been eating other galaxies. To understand galactic cannibalism, you need to think about how gravity works on the largest scales. Galaxies do not exist in isolation. They are grouped together in clusters, held together by their mutual gravitational attraction. Within these clusters, galaxies move around each other, sometimes passing close by, sometimes colliding directly. When two galaxies get close to each other, their gravity begins to distort their shapes. Stars get pulled out of their normal orbits. Gas and dust get compressed and stretched. If the galaxies are similar in size, they might merge together over hundreds of millions of years, eventually forming a single larger galaxy. But if one galaxy is much bigger than the other, something different happens. The larger galaxy simply absorbs the smaller one, stripping away its stars and gas, adding all of that material to its own massive body. This is what has been happening to IC 1101 for billions of years. As the largest and most massive galaxy in its cluster, IC 1101 sits at the gravitational center of everything around it. Smaller galaxies that venture too close get trapped by its enormous gravity. They spiral inward, getting torn apart and consumed over millions of years. Each meal makes IC 1101 a little bit bigger, a little bit more massive, a little bit more dominant. Scientists estimate that IC 1101 has undergone at least 76 major mergers over its long history. 76 times another substantial galaxy fell into this cosmic giant and was absorbed into its body. And those are just the major mergers. Countless smaller dwarf galaxies have also been consumed, galaxies so small that they barely registered as a meal for this enormous predator. The evidence for this cannibalistic history is written in IC 1101's very structure. When you look at a galaxy like our Milky Way, you see a beautiful spiral pattern. Those spiral arms are regions where stars are actively forming, where clouds of gas are collapsing under gravity to create new stellar nurseries. Spiral galaxies have lots of gas and dust, the raw materials needed for star formation, and they have a distinct rotating disk shape. IC 1101 looks nothing like this. It is what astronomers call an elliptical galaxy, which means it has a smooth, oval-shaped appearance with no spiral arms at all. Elliptical galaxies form when spiral galaxies merge together. The violent gravitational interactions during a merger destroy the delicate spiral structure, mixing all the stars together into a more random, spherical, or oval distribution. The fact that IC 1101 is an elliptical galaxy tells us that it has experienced so many mergers that any original spiral structure it might have had has been completely erased. All of those collisions, all of that gravitational chaos, has stirred up the stars like someone mixing ingredients in a cosmic bowl. What remains is this smooth, featureless giant, a testament to billions of years of galactic consumption. But there is something even more remarkable about IC 1101. Despite containing 100 trillion stars, it is actually a dying galaxy. The stars within it are almost all old. Most of them are what astronomers call red giants or yellow stars, ancient stellar objects that have already burned through most of their fuel. Very few new stars are being born inside IC 1101. This might seem strange at first. With so many stars and so much mass, you might expect IC 1101 to be a hotbed of stellar activity. But remember how it grew so large. Every time IC 1101 consumed another galaxy, it also consumed that galaxy's gas supply. Gas is the fuel for star formation. Without gas, new stars cannot be born. Over billions of years of cannibalism, IC 1101 has used up or expelled most of its available gas. The mergers themselves were often violent enough to heat the gas to extreme temperatures, making it expand and escape the galaxy entirely, or to compress it so quickly that it all formed into stars at once in brief, intense bursts of activity. Either way, the end result is a galaxy that has run out of raw material. What remains is a quiet giant, slowly fading into the cosmic night. The stars that exist now will continue to shine for billions of years to come, but as they eventually burn out and die, there will be no new generations to replace them. IC 1101 is like an ancient kingdom that has conquered all of its neighbors, but has no children to carry on its legacy. It is massive, powerful, and utterly magnificent, but it is also approaching the end of its active life. At the very heart of IC 1101 lies something even more incredible than the galaxy itself. Sitting at the center of this cosmic giant is one of the largest known supermassive black holes in the entire universe. Every large galaxy has a supermassive black hole at its core. Our own Milky Way has one called Sagittarius A-, which contains about 4 million times the mass of our Sun. The black hole at the center of the Andromeda galaxy is even bigger, containing somewhere around 100 million to 200 million solar masses. But the black hole at the center of IC 1101 is in a completely different category. Scientists estimate that it contains somewhere between 40 billion and 100 billion times the mass of our Sun. To put that in perspective, this single black hole might have 25,000 times more mass than the black hole at the center of our entire Milky Way galaxy. Let me help you understand just how massive this is. If you could somehow weigh the Earth, you would find it has a mass of about 6 trillion kilograms. That sounds like a lot until you compare it to the Sun, which is about 330,000 times more massive than Earth. Our Sun is a fairly ordinary star, neither particularly large nor particularly small by stellar standards. Now multiply the Sun's mass by 50 billion. That is roughly how much mass is packed into the supermassive black hole at IC 1101 center. All of that mass is compressed into a region of space from which nothing can escape. The gravitational pull at the event horizon, the boundary of the black hole, is so intense that even light itself cannot break free. The size of a black hole's event horizon depends on its mass. For a black hole of 50 billion solar masses, the event horizon would have a radius of roughly 150 billion kilometers. That might sound enormous, and it is. But remember that this is a region containing 50 billion times the mass of the Sun compressed into what is essentially a point at the center. The event horizon is just the boundary beyond which escape becomes impossible. To put this in perspective, our entire solar system, from the Sun to the orbit of Neptune, is about 9 billion kilometers across. The event horizon of IC 1101's black hole is roughly 16 times larger than our entire solar system. If you place this black hole where our Sun is, its event horizon would extend well beyond the orbit of Pluto, engulfing everything we consider our cosmic home. What would it be like near this monstrous black hole? The physics of such extreme environments is bizarre and counterintuitive. Time itself would pass differently near the event horizon compared to far away. Someone falling toward the black hole would see the outside universe speed up, while an outside observer would see the falling person slow down and appear to freeze as they approach the horizon. From the outside, they would never seem to actually cross the boundary. Inside the event horizon, all directions lead toward the singularity at the center. Space and time themselves become so warped that the concept of escaping becomes meaningless. The singularity, a point of theoretically infinite density, would tear apart anything that fell in, stretching it into long, thin strands through a process physicists have nicknamed spaghettification. But here is something remarkable. Despite its enormous size and terrifying properties, the black hole at IC 1101's center is currently relatively quiet. It is not actively devouring huge amounts of matter. There is no brilliant accretion disk swirling around it, no powerful jets shooting into space at nearly the speed of light. The black hole is there, waiting, but it has already consumed most of the material that was easily within reach. This quietness is actually related to the same phenomenon that has stopped IC 1101 from forming new stars. Most of the gas in the galaxy has already been used up, and without gas falling toward the center, the black hole has little to eat. Occasionally, a star wanders too close and gets torn apart, providing a brief meal. But these events are rare. The black hole, like the galaxy that hosts it, is a giant in repose, powerful but dormant. There are still traces of the black hole's past activity. Astronomers have detected a radio source at IC 1101's center, catalogued as PKS 1508+059. This radio emission comes from relativistic jets, streams of particles accelerated to nearly the speed of light and ejected from the vicinity of the black hole. These jets are powered by the black hole's rotation and magnetic fields, and they can carve out enormous cavities in the surrounding gas. Images from X-ray telescopes show these cavities clearly. They are bubbles of very hot, very thin gas blown outward by the energy released near the black hole. Some of these bubbles are millions of light-years across, testimony to periods in the past when the black hole was much more active than it is today. The energy required to inflate these bubbles is staggering, equivalent to the total energy output of billions of stars over millions of years. This kind of feedback between supermassive black holes and their host galaxies is one of the most active areas of research in modern astrophysics. Scientists now believe that supermassive black holes play a crucial role in regulating galaxy growth and evolution. When gas flows toward a galaxy's center, the black hole can release enough energy to heat that gas and push it outward, preventing it from forming stars. This creates a kind of thermostat effect that helps determine the final size and properties of galaxies. In IC 1101's case, this feedback may be partly responsible for the galaxy's current state. The black hole has helped shut down star formation by heating gas and preventing it from cooling and collapsing. The giant galaxy and its giant black hole have reached a kind of equilibrium, each one having shaped the other over billions of years of shared evolution. Black holes grow by consuming matter that falls into them. When galaxies merge, the supermassive black holes at their centers eventually find each other and merge as well. Over the course of IC 1101's long history of galactic cannibalism, its central black hole has been fed again and again. Every galaxy that IC 1101 consumed added to the mass of this growing monster. Every merger brought in more fuel for the black hole's insatiable appetite. The process by which two supermassive black holes merge is fascinating and violent. When two galaxies collide, their central black holes do not immediately find each other. They are separated by vast distances and surrounded by billions of stars. But as the merger progresses, gravitational friction with the surrounding stars causes the black holes to spiral toward the center of the combined galaxy. Eventually, the two black holes get close enough to form a binary system, orbiting around each other. As they orbit, they lose energy through gravitational waves, ripples in the fabric of spacetime itself. These gravitational waves carry energy away from the binary, causing the orbits to shrink. The black holes spiral closer and closer, orbiting faster and faster, until finally they merge in a catastrophic event that releases enormous amounts of energy. When two supermassive black holes merge, the gravitational waves they produce are among the most powerful events in the universe. The final merger releases more energy than all the stars in a typical galaxy combined, though most of this energy is in the form of gravitational waves rather than light. We have only recently developed the technology to detect gravitational waves. The first direct detection came in 2015, when the LIGO observatories measured waves from two stellar mass black holes merging about 1 billion light-years away. Since then, dozens of gravitational wave events have been observed, opening up an entirely new way of studying the universe. Future gravitational wave detectors, like the planned LISA mission that will fly in space, will be able to detect mergers of supermassive black holes. When LISA launches, perhaps in the 2030s, it might actually detect events similar to the mergers that built up IC 1101's central black hole. We will be able to listen to the universe as giant black holes collide and merge, adding another sense to our astronomical toolkit. IC 1101's black hole has experienced dozens of such mergers over its long history. Each merger added mass and altered the black hole's spin. The process of multiple mergers also affected the surrounding galaxy. As the merging black holes flung stars outward through gravitational interactions, this is probably why IC 1101's core is so large yet relatively faint. Repeated black hole mergers have scattered stars away from the very center, creating a core profile that is unusual for galaxies of this size. The event horizon of a black hole, the boundary beyond which nothing can escape, gets larger as the black hole gains mass. For a black hole containing 50 billion solar masses, the event horizon would extend outward for about 150 billion kilometers, roughly the distance from our Sun to the outer reaches of our solar system, all contained within a region of space where not even light can escape. Around this supermassive black hole, there is a bright radio source that astronomers have catalogued as PKS 1508+059. This radio emission comes from jets of material being blasted outward from the vicinity of the black hole at nearly the speed of light. Even though the black hole is not as active as it once was, it still occasionally flares to life, releasing enormous amounts of energy into the surrounding space. The presence of such an enormous black hole raises fascinating questions about the connection between galaxies and the monsters at their hearts. Scientists have discovered that there is a relationship between the mass of a galaxy's central black hole and the properties of the galaxy itself. Bigger galaxies tend to have bigger black holes. But which came first? Did the black holes form first and then grow their galaxies around them? Or did the galaxies form first and then build up their black holes over time? The answer seems to be that they grew together, each one influencing the development of the other. As IC 1101 consumed more and more galaxies, its central black hole also consumed the black holes from those galaxies. The two processes fed into each other, creating a feedback loop that produced both the largest known elliptical galaxy and one of the largest known black holes in existence. The core of IC 1101 is also remarkable for its sheer size. A study conducted in 2017 using images from the Hubble Space Telescope measured the galactic core and found that it stretches across nearly 14,000 light-years. The central core of IC 1101, not the whole galaxy, but just the innermost region, is bigger than most entire dwarf galaxies. This core alone contains more stars than most galaxies in the universe. Now I want to take you on a journey to help you truly appreciate the scale of what we are talking about. Imagine you could somehow travel from one end of IC 1101 to the other. You would need to cross somewhere between 4 and 6 million light-years. Remember, light travels at about 6 trillion miles per year. Even at that incomprehensible speed, crossing IC 1101 would take millions of years. But let us try another comparison. The Voyager 1 spacecraft, launched by NASA in 1977, is the fastest human-made object ever to leave our solar system. It is traveling at about 38,000 miles per hour relative to the Sun. At that speed, Voyager 1 would take about 80,000 years just to reach the nearest star to our Sun, Proxima Centauri, which is only about 4 light-years away. To cross the entire Milky Way at Voyager 1 speed would take about 2 billion years. And to cross IC 1101, you would need somewhere between 80 billion and 120 billion years. That is more time than the universe has even existed. Even with our fastest spacecraft, crossing this single galaxy would be completely impossible. Here is another way to think about it. If you could shrink the Milky Way down to the size of a dinner plate, about 10 inches across, then IC 1101 would be the size of a large swimming pool. Our entire galaxy, with all of its hundreds of billions of stars, with the spiral arms where we make our home, would be just a tiny dish floating in a vast sea. Or consider this. Light from IC 1101 has traveled for over 1 billion years to reach us. In all that time, light has been continuously streaming away from this galaxy in every direction. Every second, IC 1101 radiates enough light to travel about 186,000 miles. Over 1 billion years, that light has traveled 1 billion light-years, which is about 6 billion trillion miles, and it is only now just arriving at our telescopes, ancient photons that left their home galaxy when Earth was still in its earliest stages of complex life. The discovery and study of IC 1101 would not have been possible without tremendous advances in telescope technology. In the early days of astronomy, telescopes were limited by the size of their lenses and mirrors. Larger telescopes could gather more light and see fainter objects, but there were practical limits to how big you could make a telescope on the ground. The atmosphere also posed a problem. Earth's atmosphere is constantly moving and shimmering, which is why stars appear to twinkle. This twinkling blurs the images that ground-based telescopes can capture, limiting how clearly they can see distant objects. For most of the 20th century, astronomers could see that IC 1101 existed and was very large, but they could not study its detailed structure. Everything changed with the launch of the Hubble Space Telescope in 1990. Floating above the atmosphere, Hubble could capture images with incredible clarity. Over the decades since its launch, Hubble has observed IC 1101 multiple times, revealing details about its core, its surrounding halo of stars, and its relationship to the other galaxies in its cluster. More recently, astronomers have used a variety of other telescopes to study IC 1101 at different wavelengths of light. Radio telescopes have detected the emission from its central black hole. X-ray telescopes have observed the hot gas that fills the cluster around it. Infrared telescopes have peered through the dust to study the stellar populations within the galaxy. Each new observation adds to our understanding of this cosmic giant. But there is still much we do not know. The exact number of stars in IC 1101 is still uncertain, because counting stars in such a distant galaxy is incredibly difficult. The precise size of the galaxy depends on how you define where it ends, since galaxies do not have sharp boundaries but gradually fade into the darkness of intergalactic space. The mass of the central black hole is known only approximately, because measuring black hole masses at such distances involves many assumptions. What we do know is that IC 1101 represents something close to an upper limit for how large galaxies can get. There may be slightly larger galaxies out there waiting to be discovered. In fact, in 2022, astronomers announced the discovery of a galaxy called Alcyonius, which has radio lobes extending across an astonishing 16 million light-years. But Alcyonius is a special case. Its enormous size comes from giant jets of material shooting out from its central black hole, not from stars and normal galactic material. When it comes to the actual body of a galaxy, the collection of stars and gas and dark matter that make up its substance, IC 1101 remains one of the largest ever found. It sits at the extreme end of the galactic size distribution, a true monster among giants. The story of IC 1101 also tells us something profound about the nature of the universe and the passage of cosmic time. Galaxies do not form all at once. They grow over billions of years through a process of accumulation and merger. Small galaxies form first from collapsing clouds of primordial gas. Those small galaxies then merge together to form larger ones. Larger galaxies merge to form even larger ones, and on it goes, with the biggest galaxies growing ever larger by consuming their smaller neighbors. This process is called hierarchical structure formation, and it is one of the fundamental principles of modern cosmology. The universe builds things from the bottom up, starting small and growing large through countless mergers over cosmic time. IC 1101 is simply the most extreme example of this process that we have found so far. It has had billions of years and a perfect location at the center of a rich galaxy cluster to grow to its incredible size. But the growth cannot continue forever. IC 1101 has already consumed most of the galaxies that were close enough to fall into it. Those that remain are either too far away or moving too fast to be captured. The surrounding cluster is slowly spreading out due to the expansion of the universe, carrying potential victims farther and farther from IC 1101's gravitational reach. At the same time, the larger universe is changing in ways that will eventually affect every galaxy, including this enormous one. Space itself is expanding, and not just expanding, but accelerating in its expansion. This acceleration is driven by something scientists call dark energy, a mysterious force that makes up about 68% of the total energy in the universe, but whose nature we do not understand at all. Let me explain dark energy a bit more, because it is one of the most fascinating and puzzling discoveries in all of science. For most of the 20th century, astronomers assumed that the expansion of the universe was slowing down. This made intuitive sense. Everything in the universe is pulling on everything else through gravity. You would expect all that gravitational attraction to act like a brake, gradually slowing the expansion that began with the Big Bang. In 1998, two independent teams of astronomers made a shocking discovery. They were measuring the expansion rate of the universe by observing distant supernovas, using them as standard candles to calculate cosmic distances. What they found was completely unexpected. The universe was not slowing down. It was speeding up. Distant galaxies were moving away from us faster than closer ones, and the rate of expansion was accelerating over time. This discovery was so unexpected that the astronomers initially thought they had made an error. But as more data came in, from more supernovas and from other observations, the result held up. Something was pushing the universe apart, counteracting gravity and causing space itself to expand at an ever-increasing rate. Scientists named this mysterious force dark energy, though the name tells us very little about what it actually is. We know that dark energy makes up about 68% of all the energy in the universe. We know that it acts as a kind of anti-gravity, pushing space apart rather than pulling it together. We know that its effects become more important over time as the universe expands and ordinary matter becomes more spread out. But we do not know what dark energy is made of, where it comes from, or why it has the strength that it does. It might be a property of empty space itself, something called the cosmological constant that Albert Einstein once proposed and then called his biggest blunder. It might be a new kind of energy field that permeates the universe. It might even be a sign that our understanding of gravity is incomplete and needs to be revised. What we do know is that dark energy is reshaping the future of the cosmos. As space expands faster and faster, distant objects recede from us at ever-increasing speeds. There is a limit to how fast light can travel, but there is no limit to how far space itself can expand. Eventually, objects will be carried away from us by the expansion of space faster than their light can travel toward us. When that happens, they will vanish behind a cosmic horizon, forever beyond our reach. For IC 1101, this means that its days of growth through galactic cannibalism are numbered. Eventually, there will simply be no galaxies left for it to consume. It will become isolated, a lonely giant floating in an ever-emptying universe, watching as one by one the other galaxies fade from view. Let me paint a more detailed picture of what this future looks like. Remember that IC 1101 sits in the Abell 2029 galaxy cluster, surrounded by hundreds of other galaxies. These galaxies are bound together by gravity, orbiting around their common center of mass. For now, gravity is strong enough to hold the cluster together against the expansion of space. But in about 100 billion years, the expansion will have accelerated to the point where galaxies outside the local supercluster will start to disappear over the cosmic horizon. From IC 1101's perspective, the sky will start to empty. One by one, distant galaxy clusters will fade from view, their light no longer able to reach across the expanding void. The observable universe, which currently contains about 2 trillion galaxies, will shrink and shrink. Within the Abell 2029 cluster, things will be different for a while longer. The galaxies there are close enough and bound tightly enough that they will stay together even as the larger universe empties out. Over the next several billion years, these galaxies will continue to interact, merge, and evolve. IC 1101 might still consume a few more victims, growing slightly larger even as the rest of the universe slips away. But eventually, even the galaxies within the cluster will merge together. The same processes that built IC 1101 will continue, drawing the remaining galaxies toward the center, where they will be absorbed into an even larger combined structure. In the very long run, perhaps in several hundred billion years, all the galaxies in the Abell 2029 cluster might merge into a single enormous galaxy, even larger than IC 1101 is today. By that time, however, the universe beyond the cluster will be essentially empty. No light from distant objects will be reaching the cluster anymore. The night sky, if any observers still existed, would show only the stars of the local merged galaxy against a backdrop of absolute blackness. The rest of the cosmos would have slipped beyond the horizon, unreachable and unknowable. This is the isolation that awaits IC 1101 and every other structure in the universe, cut off from everything else by the relentless expansion of space. Each island of matter will be alone with itself as the eons roll by. But even this is not the final fate of IC 1101. What happens to a galaxy in a universe that is slowly winding down toward heat death? The answer is as magnificent as it is melancholy. Over the next 100 trillion years, the stars in IC 1101 will slowly burn out. The massive blue stars went long ago, exploding as supernovas or collapsing into black holes. The middle-sized stars, like our Sun, will puff up into red giants, shed their outer layers as beautiful nebulas, and then fade away as white dwarfs. Even the smallest, longest-lived stars, the red dwarfs that burn their fuel so slowly they can shine for trillions of years, will eventually exhaust their hydrogen and go dark. Let me walk through this stellar death in more detail, because the timescales involved are truly mind-boggling. The most massive stars in IC 1101, the blue giants and supergiants, live fast and die young. They burn through their fuel in just a few million years before exploding as supernovas. Any blue giants that IC 1101 once possessed burned out billions of years ago. The galaxy today is dominated by older, smaller, longer-lived stars. The stars most similar to our Sun have lifetimes of about 10 billion years. Our Sun is roughly halfway through its life, with about 5 billion years left before it swells into a red giant and eventually becomes a white dwarf. In IC 1101, many Sun-like stars have already completed this process, leaving behind white dwarf remnants. Others are still shining, but over the next several billion years, they too will burn out. But the most numerous stars in any galaxy are red dwarfs, tiny stars with a fraction of the Sun's mass. Red dwarfs burn their fuel so slowly that they can shine for trillions of years. A red dwarf born at the same time as our Sun will still be shining long after the Sun has become a cold white dwarf. In IC 1101, with its 100 trillion stars, there are untold numbers of red dwarfs. These tiny, dim stars will be the last to go out. For trillions of years after the larger stars have died, the red dwarfs will continue to burn, providing the only light in an otherwise darkening galaxy. But even red dwarfs have limits. The smallest red dwarfs, with perhaps 8% of the Sun's mass, can burn for up to 10 trillion years. That is about 700 times the current age of the universe. But eventually, even they will exhaust their hydrogen fuel and fade into darkness. Scientists estimate that star formation in the universe will effectively cease in about 100 trillion years. By that time, the gas and dust needed to make new stars will have been used up or dispersed too thinly to collapse. No new stars will be born to replace the ones that have died. The era of starlight will be over. One by one, the 100 trillion stars of IC 1101 will wink out. The galaxy will grow dimmer and dimmer over timescales that make the current age of the universe seem like the blink of an eye. Where once there was a blaze of stellar light, there will eventually be nothing but the cold, dark remnants of dead stars, white dwarfs, neutron stars, and black holes, drifting through an ever-expanding void. The universe at this stage will be a dark place, but not an empty one. All those stellar remnants, all those white dwarfs and neutron stars and black holes, will still exist. They will orbit through the merged remnant of what was once IC 1101 and its cluster companions. The galaxy will be a ghost of its former self, populated by the corpses of stars rather than by living, burning suns. But even this is not the end. Over even longer timescales, measured in years with so many zeros that writing them out would fill pages, even these stellar corpses will decay. White dwarfs will slowly cool until they become black dwarfs, objects that no longer emit any light at all. This cooling process takes an almost inconceivable amount of time. A white dwarf cools to near absolute zero only after about 10 to the 15th power years, about 1,000,000 billion years. That is roughly 100,000 times longer than the current age of the universe. Neutron stars might decay as their fundamental particles gradually break down. We are not entirely sure about this because it depends on whether protons, the building blocks of atomic nuclei, are truly stable or whether they eventually decay. Some theories of particle physics predict that protons should decay with a half-life of around 10 to the 34th power years or longer. If this is true, then over unfathomably long time spans, even the matter that makes up neutron stars and white dwarfs and planets and everything else will gradually dissolve into radiation. And the black holes, including that enormous monster at the center of IC 1101, will slowly evaporate through a process called Hawking radiation. Stephen Hawking discovered that black holes are not truly black. They slowly leak particles and radiation over immense time spans, gradually shrinking as they do so. This happens because of quantum mechanical effects near the event horizon. In the strange world of quantum physics, particle pairs are constantly popping into existence and then annihilating each other. Near a black hole's event horizon, one member of such a pair can fall into the black hole while the other escapes into space. Over time, this process drains energy from the black hole, causing it to shrink. The rate of Hawking radiation is incredibly slow for large black holes. A black hole with the mass of our Sun would take about 10 to the 67th power years to evaporate. That is a 1 followed by 67 zeros. But the supermassive black hole at the center of IC 1101 is billions of times more massive than the Sun, and the time for it to evaporate is correspondingly longer. A black hole containing 50 billion solar masses would take something like 10 to the 100th power years to evaporate, or maybe even longer. That is a googol years, a 1 followed by 100 zeros. To write out that number in full would require more paper than exists on Earth. It is a span of time so vast that everything we have discussed so far, from the Big Bang to the death of the last stars, is not even a rounding error by comparison. But even this time is not infinite. Eventually, trillions upon trillions upon trillions of years from now, even the supermassive black hole at the heart of IC 1101 will have radiated away its last bit of energy and disappeared from the universe in a final burst of Hawking radiation. When that finally happens, there will be nothing left of IC 1101 at all. No stars, no black holes, no remnants of any kind. Just the particles and radiation that once made up a galaxy, spreading out through an ever-expanding, ever-cooling, ever-darkening universe. The largest galaxy we have ever found will have followed the same ultimate path as every other structure in the cosmos, dissolving into the endless night. This vision of the future might seem bleak, but I find something strangely beautiful about it. IC 1101 exists right now, in this brief moment of cosmic history when stars still shine and galaxies still glow. It has existed for billions of years and will continue to exist for billions more. In the grand sweep of cosmic time, the era of stars and galaxies is just a passing phase, a brief flowering of complexity between the chaos of the early universe and the cold emptiness of the far future. We are lucky enough to exist during this flowering. We are lucky enough to have evolved intelligence, built telescopes, and pointed them at the sky. We are lucky enough to have discovered IC 1101 and to understand, at least in part, what it is and how it came to be. In all the vast history of the universe, stretching from the Big Bang to the final heat death, this moment right now is special. It is the moment when the universe has developed the ability to look at itself and wonder. And what we see when we look at IC 1101 is the grandest scale on which the universe has assembled matter into organized structures. We see billions of years of cosmic history written in stars. We see the results of countless galactic mergers, countless collisions, countless acts of gravitational violence that have somehow produced something magnificent. We see a monster, yes, but also a monument to the forces that shape our universe and to the processes that have been building complexity ever since the first atoms formed. Let me bring us back closer to home for a moment. Our own Milky Way is not immune to the forces that shaped IC 1101. We, too, are participating in the cosmic dance of galactic interaction and merger. Right now, as you read these words, our galaxy is in the process of consuming several smaller galaxies. The Canis Major dwarf galaxy is being ripped apart and absorbed into the Milky Way. The Sagittarius dwarf galaxy is being stretched and distorted by our gravitational pull. Streams of stars from past victims can be traced across our sky, ghostly reminders of galaxies that once existed as separate entities. And in the future, an even more dramatic event awaits. The Andromeda galaxy, our nearest large neighbor, is heading toward us. Scientists have long believed that in about 4 to 5 billion years, the Milky Way and Andromeda would collide and eventually merge into a single larger galaxy, often nicknamed Milkromeda. Recent research has introduced some uncertainty into this prediction. New studies using data from the Gaia spacecraft and Hubble Space Telescope suggest that the collision might not be as certain as we once thought. When scientists account for the gravitational influence of other nearby galaxies, like the Large Magellanic Cloud and the Triangulum Galaxy, the probability of a collision drops significantly. Some simulations now suggest only about a 50% chance of a merger happening within the next 10 billion years. But whether it happens in 4 billion years or 10 billion years or not at all, the process itself illustrates the same forces that created IC 1101. Galaxies interact, merge, and consume each other. It is the way of the universe. Even our own quiet corner of the cosmos participates in this cosmic competition. If the merger does happen, the results would be spectacular, at least on cosmic timescales. The collision itself would not be violent in the way you might imagine. Stars are so far apart that the chances of any two stars actually hitting each other are essentially zero. But the gravitational effects would be dramatic. The spiral structures of both galaxies would be destroyed. Gas clouds would be compressed, triggering enormous bursts of star formation. The two supermassive black holes at the centers of each galaxy would eventually find each other and merge, releasing gravitational waves that would ripple across the universe. Over billions of years, the chaos would settle down. What was once the Milky Way and what was once Andromeda would blend together into a single large elliptical galaxy, much like IC 1101, but much smaller. Future astronomers, if any exist, might look back at old records and marvel that their smooth, featureless home galaxy was once two beautiful spirals dancing through the void. By that time, of course, Earth will be long gone. Our sun is expected to expand into a red giant in about 5 billion years, swelling to a size that would engulf our planet. Whether humanity survives until then, whether we spread to other star systems, whether intelligence of any kind persists in the universe, these are questions we cannot answer. But the story of IC 1101 reminds us that the universe operates on timescales that dwarf individual lives, individual civilizations, even individual planets. I want to return now to the question of what IC 1101 tells us about our place in the universe. When you look up at the night sky, you might feel small. You might feel insignificant in the face of such vastness. But I think the existence of IC 1101 actually tells us something hopeful about our situation. First, consider that we can know about IC 1101 at all. A galaxy more than 1 billion light-years away, containing 100 trillion stars. And we have figured out how big it is, how it formed, what lies at its center. That is remarkable. Human beings, living on a small, rocky planet orbiting an ordinary star in an unremarkable part of an average spiral galaxy, have somehow developed the ability to understand objects so far away that their light left before complex life existed on Earth. This ability to understand is not nothing. In a universe of mindless matter and energy, of particles bouncing around according to physical laws, somehow here on Earth consciousness has emerged. Minds that can wonder, question, investigate, and learn. Whatever else we are the part of the universe that has woken up and started asking questions about itself. Second, consider that IC 1101, for all its enormity, is made of the same stuff we are. The stars in IC 1101 are fusion reactors just like our sun. They burn hydrogen into helium and heavier elements, just like stars do everywhere. The atoms in those distant stars are the same kinds of atoms that make up our bodies: carbon, oxygen, nitrogen, iron. All of them were forged in the hearts of stars somewhere in the universe, just as the atoms in our bodies were forged in stars that exploded before our sun was born. There is a continuity here, a connection between us and everything else in the cosmos. We are not separate from the universe. We are part of it. The same processes that built IC 1101 built us. The same atoms that shine in distant galaxies shine in our eyes. We are not observers of the universe from outside. We are the universe observing itself from within. Third, consider what it means that galaxies like IC 1101 can exist at all. The universe did not have to be this way. If the fundamental constants of physics were slightly different, if gravity were a little stronger or the nuclear forces a little weaker, stars and galaxies might never have formed. The universe might have collapsed back on itself moments after the Big Bang, or expanded so fast that matter never clumped together. Instead, we live in a universe where physical laws allow for the formation of stars, planets, galaxies, life, and mind. IC 1101 is a testament to what is possible in such a universe. It is proof that matter and energy, following simple physical rules over billions of years, can organize itself into structures of staggering complexity and beauty. If the universe can produce IC 1101, what else might it be capable of? What other wonders exist out there that we have not yet discovered? This brings me to the final point I want to make about IC 1101 and about our quest to understand the universe. Every discovery we make, every galaxy we study, every black hole we observe, expands our sense of what is possible. A few centuries ago, people thought Earth was the center of everything. Then we learned that we orbit the sun. Then we learned that the sun is one star among hundreds of billions in our galaxy. Then we learned that our galaxy is one of trillions. Each step has made us smaller in some sense, but it has also made the universe grander, more interesting, more worthy of awe. IC 1101 is another step in that journey. It shows us that the universe can build things far larger than we ever imagined. It challenges us to keep asking questions, to keep looking further, to keep pushing the boundaries of what we know. And it reminds us that for all our insignificance on cosmic scales, we are the ones doing the asking, doing the looking, doing the pushing. In the face of IC 1101's enormity, we can feel small or we can feel wonder. I choose wonder. As we wrap up this exploration of the biggest galaxy ever discovered, I want to leave you with one final image. Imagine yourself floating in space somewhere near the edge of IC 1101. Around you, in every direction, stars stretch out toward infinity. Not hundreds, not thousands, not millions, but trillions of stars. Each one is a sun. Each one might have planets. Each one has been shining for billions of years. You cannot see the center of the galaxy from here. It is too far away, hidden behind countless curtains of stars. You cannot see the edge either. The galaxy fades gradually into the darkness of intergalactic space with no clear boundary. You are lost in a sea of light, adrift in a structure so vast that crossing it would take millions of times longer than human civilization has existed. And yet, from a small, rocky planet more than 1 billion light-years away, beings who live for less than a cosmic instant have figured out that this place exists. They have measured its size, counted its stars, found the black hole at its heart. They have traced its history back billions of years and projected its future trillions of years hence. They have placed it in the context of an entire universe and marveled at its grandeur. That is perhaps the most amazing thing of all, not that IC 1101 exists, but that we know it does. Thank you for joining me on this journey through the biggest galaxy ever discovered. If this video helped you see the universe in a new way, please consider leaving a comment letting us know what you think about our place in a cosmos that contains such wonders. And if you want to keep exploring the mysteries of the universe with us, do not forget to like this video and subscribe to the channel. Until next time, keep looking up and keep wondering.